Hi, my name is Matt Holliday and welcome back to my Go class as we continue on talking about the types in Go. In this segment, I'd like to talk about strings. So strings are a little bit of a curious type in Go because they have two natures. Okay, we need to think about strings in a logical way and a physical way. And the reason for that is that strings in Go are all Unicode. And Unicode is a particular technique that allows us to represent international characters. So in the old days, US programming languages, they all used something called ASCII. It represented characters with 7 bits, and it basically only represented the characters of American English. So all the characters fit into 1 byte. And when we move to international languages, of course, we get accent marks and all sorts of things, and then we get non-Roman languages like Chinese or Arabic. And we need very different techniques to represent those. Unicode is a way to represent them, and it uses numbers that are bigger than what fits into a byte, right? And so there's a notion of a rune. Rune is the Go equivalent of what you think of as a character. And it's really what in some languages you would call a wide character. A rune is a synonym for a 32-bit int because that 4-byte int is big enough to represent any Unicode code point, any character, any logical character, printable character in Unicode. But in order to make programs efficient, we don't want to represent every character all the time with 4 bytes because the reality is a lot of these programs are just going to have ASCII characters. And so there's a technique for encoding Unicode called UTF-8. It's a short way of representing Unicode in bytes, which actually coincidentally was invented by a couple of the guys who also worked on the Go programming language. Years ago at Bell Labs, they developed UTF-8 as an efficient way to encode Unicode. And so when we think about strings in Go, physically, they are the UTF-8 encoding of Unicode characters. Okay, so there's another type in Go called the byte. And byte is just a synonym for an 8-bit integer. All right, a string is physically a sequence of the bytes that are required to encode the Unicode characters that are there logically, the runes. And a rune, of course, as I just said, it's a synonym for a 32-bit int. And I'm going to talk about that in just a little bit. I want to switch to the laptop because I want to demonstrate this concept of bytes versus runes. And I'm going to do that in the playground. I'm going to create a string, and I'm going to use a non-ASCII character. I'll just use the French accented E, elite. And I want to ask, when I print this out, okay, first of all, I want to get the type. So we're going to put a type in here, and then we're going to get the actual value. And when I run this, it's going to tell me that I need to do the trick I just did a minute ago. It's going to tell me that S is a string and its value is the printable characters that I typed in my program, the word elite with the accented E. Okay, that's great. And that's very useful. So when I go and print a string, I get the Unicode output. I want to ask, though, what does that look like in another way? And I'm going to cheat. I'm going to introduce something that I haven't really talked about yet, which are slices. Okay, actually, just copy all of this down here. What I want to do is I want to cast S. I want to take my string and I want to cast it to a sequence of runes. And this notation will do that. And now when I run the program, I'm going to get slightly different output because it's going to say that S, this cast version of S, is a sequence of 32-bit ints. Well, that's what a rune is. A rune is a 32-bit int. It's a Unicode code point. And I get 5 values. That's fine. I had a 5-character string. That makes sense. I want you to notice, though, that the first value down here is 233. Now, I said ASCII characters fit into the range of 0 to 127. 233 is not going to fit into that range. And so what actually happens is when this gets encoded to UTF-8, there's an expansion. So I want to add one more line, and this time I want to look at S, but I want to force it to be a sequence of bytes. And now when I run the program, my third line says it's a sequence or a slice of uint8s, 8-bit integers, okay, bytes, And there's 6 of them, not 5. And the reason for that is this first value. So if I start looking at these, if I look at it backwards, the last 4 things in here, in each one of these, are the same. The LITE, that's the same. But this first value, 233, is now being represented by 2 bytes. And that's just part of how UTF-8 encodes Unicode. Instead of using 4 bytes for every character, there's special encoding when characters get over certain sizes. If I did this with Chinese, and I'm not going to try to type Chinese right now, I don't know how, but I can put Chinese characters into here. I can do that in the playground, I've seen it. And the Chinese code points tend to be numbers like 20,000 something. So they're big. They take 3 bytes to represent. So if I had a string with some Chinese characters, you would see, like 5 characters become 15 bytes because each one of those characters represents 3 bytes to do that in UTF-8 encoding. Now, why does this matter? We have to ask the answer, what is the length of a string? We have to ask the question, I'm sorry. What is the length of a string? And when we ask the length of a string, we're going to get the physical answer. A string has 6 bytes in this case, right? I can do that by putting one more thing here. So I'm going to add one more thing on the end here. So we're going to simplify this. Hold on. All right. Right, so I'm going to go ahead and assign that converted version of the s to a variable and run that. And what I get now on this last line is, yes, I get that it's a 6-byte thing, and the length of B is 6 bytes. Now, what about the length of S? When I run that, on this first line, remember the first line said it's a string, and it's a string with the characters elite, and I see 5 characters, but the length is also 6. And that's because the length of a string in the program is the length of the byte string that's necessary to encode the string in UTF-8. So it is physically 5 printable characters visually, but it is logically 5 printable characters. It's physically 6 bytes in UTF-8 encoding, and so the length of the string is 6. And that's why we had this dichotomy. And that's the right answer, because at some point when we're running our program, we actually have to deal with the actual memory. And so it just makes more sense to ask the length of the string, how many bytes, because typically that's a bigger number. Okay, so again, the length of a string is the number of bytes required to represent the Unicode characters, not the number of Unicode characters. There's another way to do that with the strings library. So now I want to go back to the slides for a second because I want to talk about how strings are actually represented in memory. Okay, and what we have over here is a picture of some memory, and in it I have the string hello, world that I created down here. So my first little declaration down here in the corner created a variable s, and it's holding hello, world. Now, what is S? And the answer is S is actually this thing. And I want to call that a string descriptor. It's not really a term in the Go language spec, but it's a term I find useful. A descriptor, it's not exactly a pointer, right? A pointer just points at something. A descriptor describes something. It has a pointer within it. Okay, so it has a pointer to the actual location in memory where these bytes are, and it has additional information. In this case, it's the number of bytes that make up that string. Now, notice when I get to the end of the string here, there is no null byte, right? If you look at some languages, you have to end every string with a null byte. And the way you find the length of the string is you have to literally walk all the way down the string to find a null byte, which is not terribly efficient. So in Go, the length of the string is encoded in this descriptor, which you don't see. When you deal with strings in Go, you never see that descriptor. It's behind the scenes, but it's always there. Okay. When I create this next variable, hello, I'm indexing part of the string, and hello actually points to the same characters in memory. I can reuse that storage because these strings don't have a trailing null byte, and because they're immutable. They can't change once they've been laid down. So it's perfectly okay for S and hello to share storage, and in fact I've got a third variable, world, which is another part of that string S. So hello and world are strings of their own, but they are substrings in S, and they're reusing the memory that's in S. when we talk about assigning a string, so let's suppose I have a new string t, and t is s, right? So t is initialized to the same value of s. What I'm actually doing is t is just going to be another copy of this thing down here like s, and I'm just going to copy the values from s into this little descriptor for t. So t will have the same length and a pointer to the same bytes. But t is a different descriptor than s. Let's look at a few of these little operations here. If I assign the quick brown fox, I initialize the string s with the quick brown fox. So again, there's s, and s has this little descriptor, and it points to some bytes that represent the quick brown fox. Now, I'm going to look at those in several ways. So what's the length A? Well, that's 19. How many characters? And I'm cheating a little bit. I'm just assuming this is ASCII. 1 character, 1 byte, just to make things easy. All of these other little operations here, B, C, and D. So B and C are just going to be like the hello and world on the last slide. They are descriptors that point to part of the storage that S uses. They all overlap. When I create D, D is going to point to some completely different memory. D is going to be a descriptor, some new memory. It's going to have parts of S copied into it, but it's going to have the word slow instead of the word quick. So D is going to read out the slow brown fox, but it's going to do it in a different place. Okay, and the next thing I already showed, this operation we can't do. I can't change part of the string S once it exists. But this last operation is interesting, and the plus equals operator is primarily for numbers. It's an operator that says, hey, add this thing and then assign back. So it's just a little squashed, easy operator. It's the same thing as saying S equal S plus the string ES. It's the same thing. Now, how does that work? Well, the answer is, remember, S itself is this descriptor, and so we're going to take the original memory of the quick brown fox. We're going to create a new chunk of memory that's a little bit bigger. We're going to copy the quick brown fox into the new one. We're going to add the letters E and S at the end, and S is going to get changed to point to this new block of memory that has E and S at the end. Okay? The original string, the quick brown fox, doesn't change because remember, I still have these other things like C and D. C and D are still pointing at the same memory that S used to point at. So this quick brown fox thing doesn't go anywhere. It doesn't change. S is now going to point to a completely new string just like D did. D pointed to a new string that had parts of S copied into it. S is going to put a new string that has parts of the old S copied into it and some more text added on the end. And the last thing I want to show real quick is there are a bunch of string functions. I'm not going to talk about them all. There are an enormous number of string functions. So we can do things like, is this one string inside of another? Does a string start with a certain string? Does it end with a certain string? But there's one I want to call out here. And again, this is just like what we saw in the last slide. I want to turn S into uppercase. So I call this function toUpper, which changes all the letters of S to uppercase, but it does it again in a copy because the original S isn't allowed to change. So there's an S out there that has a string in lowercase, and we're going to create a new string by taking those letters and making the uppercase versions of them, but in a new piece of memory, and we're going to assign that new piece of memory back to S. So S is going to point at a different block than it used to, and it's going to have, of course, a string. Well, actually, I wrote it out here in the comment. But it's going to be a different location. Now, Go is a garbage collected language. If nobody else is using the old string, it will eventually get reclaimed. The garbage collector will pick it up and throw it away. But we're not modifying the original string in place because, again, we can't do that. Strings are immutable. Okay, so now I'm going to go into Replit again, and I'm going to write what is probably the world's simplest search and replace program. And I'm going to demonstrate some things about strings by doing that. So here it is. I'm going to once again import some things that I need that are not here. So we'll just go and start with them. And, you know, the editor will complain that we don't need them or we're not using them yet, but we will in a moment. I'm pulling in OS because I want to get arguments off the command line. We're going to write this program so it takes a couple of arguments. the thing to look for and the thing to replace it with. And we're also going to be very, very simple here and just assume that these are words of their own. They probably have spaces around them. We're not going to do anything complicated at all in the running of this program. So it's trivial, but it'll demonstrate some things about strings. So the first thing we need to find out is, do we have, in fact, some arguments? And if we don't, we're just going to stop. Because the alternative, of course, would be that we, didn't like that. Okay, so the alternative would be that we try to index an argument that's not there and fail. So we'll initialize a couple of strings here. And remember, the first argument is always the name of the program. So we're looking for the second and third, and we'll call them old and new. The other thing we're going to do is we're going to create a scanner. We're going to call something out of buff.io, and a scanner is simply a buffered I/O tool around the standard input, and by default, it's always going to split the input somehow. By default, it's going to split by lines. So as we go through here, it's going to feed us one line at a time, and it'll be efficient. If the input were very large, it wouldn't read the whole thing in. There are ways to do that. I can read an entire file in Go as a sequence of lines, but I don't normally want to do that. So instead, I'll write a scanner. Now, what's interesting is scan.scan is a function that will do the scanning, and if it succeeds, it will return true. So I can run this for loop, and my for loop is really acting like a while loop. So while scan.scan returns true, I'm going to keep going around in the loop. So this is another example of a simple for loop. Now, I'm going to split my string. So I get this line of text, and I'm going to turn it into a bunch of words. And I'm going to do that around the old string. And then I'm going to put it back together again using strings.join. I'm really not typing well today. Using the new string. So what I did is I had this line of text, I burst it around the old string, I'm joining it back together, those parts. Wherever I have several parts, that means in between there was the old string, and I'm going to put the new string in there and put it back together again. So, and then I'm just going to print out the result on one line. And that is not a whole lot of program, okay? I didn't say this was going to be a very glorious search and replace tool. But what it's going to do, again, it's going to read one line at a time. So scan.scan reads the line, tells us there was a good line, and scan.text gives us back the actual line. There are other options, and we'll see those later. There's a buff.io option that I could have the scanner scan by word, presumably like space delimited word, instead of by line. All right. So what does strings.split give us? Well, it actually gives us back a slice, and then we feed that slice into join, because join takes a slice. And then what we get back out of the strings.join is, in fact, another string. So we basically, on one line at a time, we're going to substitute out the old word for the new word. Or I should actually say, we're going to substitute the new word where the old word occurred. Now, I have in here a file, and all I did was write some very simple words here, okay, that we can use to substitute. So I'm going to feed this text file in. That'll save me retyping it over and over on the command line. So I'll do go run dot. And what I need to do now is say I'm going to replace Matt with Ed. And I'm going to do that everywhere in test.text as the input. And there we go. We got the output. Instead of Matt went to Greece. So here's my original text file in the middle. And on the right, we can see where the word Matt occurred, it now has Ed. Now, it's possible that this would have worked if I'd also left out that space, and let's give it a try and see if that really does work. So we'll try that. And it actually did work. So it doesn't really matter whether there's spaces or not. It will find the string. Now, of course, it's also case sensitive. So the words in here were lowercase, and the words I gave it on the command line were also lowercase. Okay, so let's go back and look at the program for 1 sec. I don't think there's anything really interesting in here. We looked at the length. We already talked about things like print line. On this line here, I initialized 2 variables at the same time. Now I can do that. It's not very common. I did it here to save space. It's more common when you initialize 2 variables because those 2 variables are the output of a function or expression that actually returns 2 things at once. We saw that in the last program. We actually called a function that returned an integer and an error, and I forgot to point out we ignored the integer by putting an underline. I'll come back to that. But we had a function that returned 2 values, and so we had 2 things on the left of the short declaration operator. But I can just do that with 2 values on the left and 2 values on the right. It's also a good way to swap. If I want to swap, I can literally say x comma y is short declared as y comma x or something, and swap the values. So this is perfectly legal. And of course, I've got another one here. So in this case, I'm using the short declaration operator because I'm not giving these the default values like I used in the last program where I used var. I'm actually giving them the value of something. And the same down here. Okay? So that's the whole of this short program. Again, it's just a little demonstration program with strings and not terribly complicated. Okay, so that was a very brief introduction to strings. We'll use them a lot. We may talk about other aspects of them, but I wanted to bring out, so in a lot of ways we think of strings as a simple type, but they're actually not. There's a bit more complication. And I wanted to illustrate this concept of the descriptor. I wanted to explain immutability, and I also wanted to explain the logical and physical distinction.